So today our speaker is Juan Maldacena, who is one of the most renowned theoretical physicists in the world. So it's a real privilege to hear from him today. So Juan got his undergraduate and his master's degrees in Argentina, in Bariloche, in Argentina, and then came to Princeton University to do his PhD. Actually, we were contemporaries and know each other from graduate school. And then he went on at the end of his PhD to write a magisterial PhD thesis on, indeed, black holes and the structure of space-time, or questions related to black holes and the structure of space-time. In the 20-some years since then, Juan has written many seminal papers in the quantum theory of gravity, about the nature of space, about the nature of time, the physics of black holes, the very early universe, and really transformed our understanding of theoretical physics in the process. So it's a privilege to hear from him today, and there you go.
So thank you. Let me get this on. Just a second. Okay. It's a privilege to be here. I've been having a lot of fun here in the Aspen Center for Physics, discussing physics. I actually have a connection to Heinz Pagel that comes with a funny story. Our house was someone broke into our house, and the police dispatched, the police went in, and then we were not there, and the police reported that they found a woman there that claimed to live there in our house. And we said, no, you should arrest her. She's not living there, it's none of us. But it turned out that the police made a mistake and went to the wrong house. 3 houses over, that's the house of Elaine Pagels. That's Heinz Pagel's wife. Okay. Anyway, so this is a talk about black holes and the structure of space-time. And well, it's not working. Oh, I forgot to put in this in. Sorry. So first I'll give you a very short outline. So general relativity predicts black holes. Schwarzschild found this solution. People were very confused about the solution. Einstein was confused about the solution. And it took many years to really understand the solutions. Einstein thought that they were unphysical solutions. And then eventually it was understood that they were unavoidable solutions that arise when you put too much matter in a small region of space-time. And they were called black holes. Then Hawking realized they're actually not black. You can have red black holes, white black holes, and we'll try to understand that. So even the name was wrong. So black holes have been always a source of confusion and also a source of new physics, surprises. And so Hawking thought that this phenomenon implied that black hole quantum mechanics is incompatible with gravity. And then through the methods of string theory, we think that black holes, as seen from the outside at least, are compatible with quantum mechanics. And this led also to some relationship between quantum mechanics and the space-time geometry that we'll be reviewing. But there are still many confusions that remain, and recently there were interesting papers highlighting those confusions. Okay, so let's start with the basics. There is something called the principle of relativity, which is a few hundred years old, that says that an observer traveling with constant velocity observes the same laws of physics as an observer at rest. So you have 2 observers. If each is in his or her own laboratory, they cannot notice whether one is moving or the other is stationary. Now, Einstein put a new twist in this principle by saying that there is one aspect of the laws of physics, which is that the maximum velocity for signal propagation is the speed of light. And that maximum velocity should be the same for all observers. So it's the same principle, but with one new element. And this element has an interesting consequence. So imagine that you have 2 observers, and they are both trying to, this is some light signal. Now, from your intuition, you would think that this one would see the light signal propagating faster than this one, right? If that's not your intuition, I'm not explaining this clearly. So it seems that it would be impossible for, naively we would say that it would be impossible for this observer to see this propagating at the same speed as this one. And indeed, you need something quite radical for that to be the case. You need that the time that that time runs more slowly for this observer. And then he can see the light propagating at the same distance. In addition, the observer is kind of contracted in the direction of propagation. That's why I drew it this way. So that's what Einstein derived from this principle of relativity, and this is what is called special relativity. This is the Einstein theory of special relativity implies this in particular. And it implies some other things. For example, there is the famous twin paradox. Imagine two twins that are born at the same time, and then one twin travels very far, and the time flows slowly for him. And then they go back, and when they go back, the one that was traveled very far is younger. Now, you might say, well, how do I know which of the one was the one who traveled? And there is a difference between these two twins, and one difference is that this one felt some acceleration. So we could apply the special relativity formulas while they were moving with constant velocity, but there was some moment when they felt some acceleration. And so the one that felt some acceleration is a little younger. Now imagine that we have the following setup, that the two twins are born, one goes away and comes back, and when they meet again, they die. Okay, that's the rule. Sorry for the bad rule, but let's say this is the rule. Now, which of the two twins would you rather be? Would you rather be this twin or that twin? I think you clearly would rather be this twin who had a longer life. Okay. Now, it turns out that even elementary particles prefer this. So there is a principle in physics that says that any elementary particle tries to travel in a way that maximizes its own proper time. So the time it experiences is as long as possible. So that's the principle of maximal life or maximal experience time, and particles try to move in this way, and that's why particles, that's how we explain that particles move along straight lines. So the lesson of this is that space and time form a single entity, which is space-time, and the time we measure depends on how we move. So what an observer perceives as space or as time is different, but they all perceive the same combination, which we call space-time. And particles move in straight line in that space-time to maximize their lifetime. So that's flat space. Now we go into some topic which looks a bit different at first. That's gravity, and then we'll find the relationship to space-time later. So gravity, of course, the intuition is that heavier objects fall faster, but Galileo realized that everything falls in the same way once we remove the effect of air resistance. And this observation led to Einstein, what he called his happy thought. So his happy thought was the following, was that when you fall freely, it looks as if gravity disappears. It looks as if you're floating. So the image he used was that if you are in an elevator and the elevator is falling, you would feel that you are floating in the middle of the elevator. So it looks as if gravity has disappeared for you. And the reason is that, well, one explanation, Galileo's explanation, would be to say that both the elevator and you are falling in exactly the same way. And Einstein promoted this to a kind of new physics law, which he calls the equivalence principle. So the idea that when you're falling freely, it seems that gravity disappears. That's what it says. It says the same as the happy thought. And the idea is that gravity should obey this principle somehow. The theory of gravity should obey this new principle. And so, well, that's we see this with the astronauts. They're both somehow orbiting the Earth in exactly the same way, the astronaut and the spaceship, and they feel weightless. Okay. And he realized that this principle led to the idea of general relativity, and to the idea that gravity is due to the geometry of space-time. So the theory of relativity is based on the idea that gravity is due to the geometry of space-time, and that if you have a heavy object, it produces some curvature, so the space-time is somehow curved. And then if you have a second light particle, it would follow the trajectory of maximal lifetime in that curve space-time. Okay, so now when we say that gravity deforms the shape of space-time, we usually picture this somehow the space is deformed, right? And that's correct. But in addition, something very important, and will be very important for what we're going to say, is that also the way time flows is deformed. So imagine you have a person in the top floor of a building and a person in the lower floor of the building. Each one has a clock. These are two identical clocks made in exactly the same way. Then what will happen is that the clock in the bottom of the building will go a little more slowly than the clock in the top of the building. And this is a very tiny effect for an ordinary building. So it's a part in a 10 to the 15. So it's you need a super good clock to do this. But people have this clock. So there's in Colorado, they have in the NIST, they can make clocks that can detect a difference in height of 3 centimeters. So, so now we can have something similar to the twins paradox. We can have a person who stays near a high gravitational field will be younger, right? And that person is accelerating more. He's feeling a force of gravity, we say, and the same effect that we had when he was traveling and then coming back. Now, Schwarzschild, very soon after Einstein proposed his equations, Schwarzschild solved these equations in the outside of a massive spherical body. So imagine you have a massive spherical star, and outside the star there is no matter, and you can solve the equations, Einstein's equations, outside the star. And this is a full geometry, and this geometry in particular will tell us how time flows for an observer who's sitting at a fixed radial position. So for example, if you have someone sitting at the surface of the star, its clock will run a little more slowly than the clock very far away, right? Where there is, so this feels some weight also. This observer feels a certain weight. The observer very far away feels no weight. Okay? Now you can imagine that the star is smaller, but with the same mass. Imagine that same star, and we make it smaller and smaller. So we're going to do that. We're going to follow this process of making the star smaller and smaller. So we make it a little smaller, then the person will feel a larger weight, and that his time will run a little more slowly. And then something very surprising happened, which is that if you make the star smaller than a certain radius, smaller than a certain size, it looked as if the person would feel here an infinite weight. Okay? Someone sitting at that position will feel an infinite weight, and his clock or her clock would stop completely. Okay? And this is what surprised Einstein, and thought that this was something unphysical. That in a real physical process, this will never happen. And not only Einstein, but most of the people thinking about this thought in the beginning that this was some unphysical feature. But yeah, yes.
In this experiment, the weight of the star is the same in each point.
Yeah, the total mass of the star is the same.
Okay.
Yeah, we are taking the same mass,
yeah,
and we are making it smaller and smaller. Yeah. Any other questions? Well, now something we should realize is that those observers were not falling freely, right? Remember Einstein's happy thought. The idea was that if you fall freely, gravity disappears. So the question is, what happens with those people if they were to fall freely? Okay? And it turns out that what happens is that they actually fall freely, and they can go through that surface where someone who would be sitting at fixed radial position would feel an infinite weight. If you fall freely, you don't feel anything special as you go through that part of the space-time. So this is the same diagram of that geometry. We have the outside geometry. We had this surface that is now called the horizon, the surface where a static observer would feel an infinite weight. But the falling observer doesn't feel anything special. And then when you go through that, you find a new region of the geometry. And the new region of the geometry has a slightly different character. It looks like a collapsing universe. It looks like a big crunch universe. And that whole region of spacetime collapses into what we call a singularity. So a region where the spacetime curvature becomes very large, and where if you fell there, you would be destroyed. So your head would go in one direction, your feet in another direction. So it's not a pleasant process. But the important point here is that you don't feel anything at the horizon. You feel something a little later. So you fall in and go through the horizon. And one problem is that once you go through the horizon, it's called horizon because once you go through it, there is no way of going back out. So no matter what rocket you have, you cannot, even Elon Musk cannot make a rocket that can go out of the black hole. So because the singularity, this space-time looks like a big crunch, and the singularity is in your future. In the same way that you cannot travel to the past, you cannot avoid falling into the singularity. So the singularity is in the future, and it's not really, we should not think of it as inside the black hole, like in a spatial point. It's really in the future of that region. Now, there is a nice analogy that was proposed by Bill Unruh, which is to think of this space-time as a river. So imagine you had a river where we have water flowing to a waterfall. So a waterfall would be analogous to the singularity. And then on this river, there are some fish. And the fish can travel at some maximum velocity. And that maximum velocity is analogous to the velocity of light. So here in this region, the velocity of the water is less than the velocity of light. And if a fish swims in that direction, that fish can swim upstream and can avoid falling into the singularity. But a fish that is sitting at this point, the velocity of the river becomes equal to the velocity, the maximum velocity at which the fish can swim. And if a fish is swimming there, it would just stay there. That's analogous to these clocks that stop at some special position when they're. And if a fish happens to go into this region of the river, where the velocity of water is bigger than the velocity of light, the fish cannot avoid falling into the singularity or the waterfall. But something important is that if you're a fish in this river, and let's say it's a muddy river, you cannot see the shore, you cannot see the banks of the river, then you don't realize that you passed this point. There is nothing special at this point in the river. So a few things were learned. Once is that once you cross the horizon, you cannot get out. And then another thing that, took some time to understand, but was eventually understood, is that a star can collapse into a black hole. So if you have a very massive star, it can collapse into a black hole. And also that there are objects in the sky that seem to be black holes, the black holes we are talking about. So these black holes we are talking about here arose just as solutions, mathematical solutions of Einstein's equations, but we think that there are objects in the sky which are actually those physical objects described by those equations. And the real black holes that we think exist in the universe come in two types. Some are produced by the collapse of massive stars that have some sizes that range between 10 and a couple of 100 kilometers. And then there are black holes at the center of galaxies which have a much bigger size. They have a size of the solar system. They are very massive. And so you can ask how do we see them? So one method is that when you have a black hole and some matter falls into the black hole, the matter becomes hot as it falls into the black hole and emits certain characteristic radiation that one can see, and astronomers interpret it as a signature of a black hole. And more recently, people have observed the gravity waves produced when two black holes collide. And these signals of gravity waves are in nice agreement with what you expect from Einstein theory. So this is an example of the first process. So we have here, this is for very big black holes of the size of a galaxy. So here we have the galaxy, and in the center we have some amplified image. Here this is 400 light years. The black hole would be a very tiny dot there in the center. The size of the solar system is just a few hours, so 400 light years is much bigger. But here we see the matter falling in. Some of the matter falls into the black hole, it heats up, some of it comes out as jets and so on. And so you have this very compact, very small object producing these huge, humongous structures in the galaxies. So this is one type of black holes. And most recently, a couple of years ago, there are these gravity wave detectors. There are a couple here in the US, there is one in Italy. And when black holes collide, they produce gravity waves, and these gravity waves can be detected by these gravity wave detectors. And the shape of the gravity waves is exactly the one that is predicted from Einstein theory if you assume that the two objects that collide are black holes. So this is currently one of the best evidences for black holes, because the shape of these gravity waves is sensitive to the geometry very close to the horizon of the black hole. Now, maybe I should ask for questions now, and because now we're going to start discussing some more theoretical aspects. Yeah.
The pictures that you showed, were those artists' renderings? Or
This is an artist renderings. No, these are actual pictures. Yeah. Okay. Any other question? Yeah.
That's probably not too important in this discussion, but what causes the jets?
Yeah, that's a more complicated astrophysical question that I don't know, but the idea is that some of the particles that fall in, eventually, it's like they bounce back and they go up. The black hole is spinning, that's why there is a special axis, and some particles end up going in those directions. Any other question? Yeah.
Yeah. What else happens besides gravity waves when two black holes collide? Do they become one black hole?
Oh yes, they become one black hole. Yeah, once they collide, they soon become one spinning black hole. Mm-hmm. Yes. Mm-hmm.
So if I was to take a spaceship,
Yes.
and so could it go around like a black hole? So
Yes, yeah, it could go around the black hole. So if you don't cross the horizon, outside the horizon, the geometry is the same as the geometry outside a massive body. So if we were to replace, for example, the sun by a black hole, we would continue orbiting that black hole, the same way that the Earth is orbiting the sun. And you could get closer, but you have to aim well, because if you go through the horizon, then you can't come back up.
question, so like,
Yeah.
is a black hole like a ripping space?
Well, there is some singularity in the interior. You could call it a ripping space. It's a region where the curvature is very large. Yeah, but that's inside the horizon, so we don't see it from the outside. From the outside, we see a kind of hole, a bottom, like a well. Imagine a water well, right? Very deep, and you can throw things in, they just fall in. Nothing happens, but if you were the one that fell in, then something would happen to you. Yeah.
In the ice cube,
Mm-hmm.
I guess, station in
Yes,
Antarctica.
yes.
They recorded an event
Yeah.
with 290 trillion electron volt neutrinos.
Yes,
I think there
yes.
were 14 of them, 2 different batches.
Yes.
And then attendant to that, but afterwards, you had some 400 billion electron volt gamma rays. Now, do you think that, I mean, it was probably from the polar regions, but
Mhm.
do you think that was like really an event like right on the quote event horizon, or what kind of proximity would you think there would be for something like that?
Well, I don't know the details of that. So of these high energy gamma rays, I think one theory is that they could be produced by explosions of stars. Maybe they are produced by some black holes. There is some connection between these high energy cosmic rays and active galactic nuclei, which are these black holes that I shown in the previous transparency. Yeah, so I don't have a detailed answer to your question. Yes.
When you say a singularity
Yes.
is at the center,
Yes.
singularity, I think, usually means that the mathematics break down.
Yes.
And they do not describe what's going on there.
Yes.
Do you have any math that attempts to describe what's going on?
No, we don't. We don't have a mathematics that describes what happens to you when you fall in. So I mean, we can say that you will die, because for that you don't, yeah, because because the mathematics holds close enough to the singularity where the gravity forces are big enough for you to die. But you can ask whether what happens afterwards. Is there another region of space-time afterwards? Does time end, and so on? And we don't have an exact description of the interior of the black hole. So the descriptions we have are mostly from the exterior of the black hole, and that's one of the things we are trying to understand now. So the area of the horizon of the final black hole is actually bigger than the initial black hole. And this is a very simple property of very complicated equations. And physicists we always like when we find some simplicity and some complexity. So we have very complicated equations and this very simple equation. So that was an interesting equation. And that in particular says that this final black hole cannot have a zero mass, for example. You cannot have a situation where the two black holes collide and all their initial energy is emitted into gravity waves. I mean, part of the initial energy of the black hole is emitted into gravity waves, but it cannot be all of it, because the area of the final black hole has to be bigger than the initial areas. So far we've discussed black holes according to Einstein theory, or general relativity, which is a classical theory. And these black holes are really black, in the sense that they don't emit any light, as you were saying. But once we include quantum mechanics, we find the new surprise. And that's that we can have white black holes, funny situation. So Hawking found that black holes emit radiation, and the temperature of the radiation increases as the size decreases. So if you have a smaller black hole, the black hole is hotter and will emit the radiation with shorter wavelength, higher temperature. And if it is small enough, you can see it red. And if it is even smaller, you can see it white. Here I plotted the temperatures for black holes for various masses. So if you had a black hole which had the mass of the sun roughly, which is these are the types of astrophysical, the black holes that are produced by astrophysics, the temperature would be very tiny. This is a very, very tiny temperature. These are degrees Kelvin, so above absolute zero. And this temperature is so small that it cannot be measured. So this effect has not been measured in black holes that have been produced. But we could imagine a black hole which is, so you can ask, what about the black hole, which black hole would emit white light? You would have to have a size which is comparable to the wavelength of light. And so we have roughly to have the size of a bacterium. And such a black hole has still a very pretty big mass, the mass of roughly a continent. And that would look white. And you would actually be able to see it. So if you had such a black hole, it would be very tiny white light. So it really would look white to your eyes. I made a little model once, but I didn't bring it this time. It emits very little power, about a little less than a microwatt. Now let me explain a little bit why. So, and this is the answer to your question. So why is this the case? So the idea is that in relativistic quantum field theory, particles can be created and destroyed. And even in the vacuum itself, we can think of the vacuum as containing particles that are created and destroyed, and in pairs where one has positive energy and one has negative energy. But in quantum field theory, there is a rule that says that all energies should be positive. But somehow this rule is enforced by some policemen. But these policemen are subject to the uncertainty principle, the quantum uncertainty principle, which says that they cannot measure the energy in very short times. So they cannot make precise measurements of the energy over very short times. So over very short times, you can have some negative energies, and the policeman cannot really check that the energies were negative, so they allow those things to exist. This is a rough picture, by the way. So in flat space, they can exist for the negative energy can exist for a short time, and they should quickly annihilate. But in the presence of a horizon, there is a new phenomenon, which is that what is energy for the outside observer is something else for the inside observer. It's more like a momentum. So it's something that could be negative. So the notion of energy for the policeman inside is different from the policeman outside. And for the policeman inside, this object with negative energy, so something that is negative energy from the point of view of the outside, is perfectly legal. And this policeman has no problem with it and allows it to exist. And this is roughly the mechanism by which black holes emit radiation. So you create these pairs as you are constantly creating, but due to the different enforcement rules of positive energy, this negative energy particle can exist perfectly well inside the black hole, but and so it can fall in, and the other one can go out to infinity. Now, this implies that the black hole will have an interesting life. So the black hole emits radiation as it loses mass. It will have a finite lifetime, and so a black hole of the mass of the Sun or the Earth will live much longer than the age of the universe. A black hole that is made with an object with an ordinary mass, let's say 100 kilograms, will evaporate in a time much shorter than a fraction of a second, and will emit an amount of energy worse than a nuclear bomb. So the process can be very quick at the very end. And if you had a black hole roughly of the mass of a mountain, so produced at the beginning of the Big Bang, then it might be evaporating now. And finally, there could be very tiny black holes producing particle accelerators, and those would decay very quickly by these processes. Now, no black holes were detected in any particle accelerator currently working, but this is just a theoretical possibility. Okay, any questions so far? Yes?
Could you have the reverse? You have the negative on
No.
energy on the inside and the positive on the outside. It doesn't flip-flop.
No, because the policeman outside really checks positive, that the energies are positive outside. And that's what he's checking. Yeah. I mean, you could have a tiny process where you have a little bit of negative energy outside that you would have to quickly annihilate. It would be like the things you have in that space. So only in the case that you have a positive outside and negative inside, you have the possibility of it going far away. Okay, let me continue. So this fact that black holes emit radiation poses some interesting theoretical problems that I'll try to describe. And I will describe really two problems. One question is, why are black holes hot? So what makes this heat for black holes? And the second one is the issue of information loss. So now, how do we explain temperature? So when the way we explain temperature goes back to the 19th century, and it's by the motion of microscopic constituents. So the air feels hotter because the molecules in the air are moving faster. So that's how we explain heat in physics. And it's the same for anything that is hot. So something that is hot, their constituents, their elementary components are moving faster than the same object when it's cold. So the question is, what is moving in a black hole? Why? What are these elementary constituents that give rise to the temperature? Now, in thermodynamics, there is a related concept which is called entropy. And this is a slightly more subtle concept which tells us how many microscopic configurations the system has. So, for example, in the case of the molecules of the air, in how many positions they can be. And this you can calculate, you can in principle measure in an ordinary system by measuring heat flow. By knowing how heat flows in and out of the system at various temperatures, you can actually measure this entropy, how many states or microstates, microscopic configurations the system has. Those are standard formulas of so-called statistical mechanics. So for a black hole, we know the mass, and Hawking gave us a formula for the temperature as a function of the mass. And from this, we can calculate these heat flows, and we can calculate the entropy. And one finds that the entropy is equal to the area of the horizon. The area of the horizon divided by the Newton constant and h bar, and this is some combination which turns out to be the so-called Planck length. So it's a very tiny length, 10 to the minus 33 centimeters. This is a very, very small length. So just to give you an idea, our size is to the minimal size we can measure experimentally, as that minimal size is to the Planck length. Okay? It's a very tiny length. We can't currently examine those tiny lengths, but what this is saying is that if you have an object with a macroscopic area, let's say 1 centimeter square, then this would be a huge entropy. And it's an entropy which is much bigger than the entropy of any object with the same area. But something interesting is that now we have an interpretation of that same area law that Hawking had found before, which is that we can view it as a consequence of the second law of thermodynamics. So the second law of thermodynamics says that the entropy increases. Now this is perhaps one of the most intuitive laws in all of physics. So entropy is a measure of disorder. And you are very used to the fact that left alone, disorder always increases. Right? And so that's what entropy, that's the general law of thermodynamics, saying that disorder always increases. And the area law that comes from Einstein's equations. So this should be somewhat surprising, because this should be very surprising, because Einstein's equations are deterministic equations. They are equations that they don't know anything about disorder, apparently. They are just, you give some initial conditions, you evolve, and the classical equations, and they nevertheless somehow know about this laws of thermodynamics. Now, when we ask about the constituents of a black hole, we are really asking about the microscopic constituents of space-time, because black holes are very universal. They don't depend on the specific matter that we have. As we saw before, the final configuration of a black hole doesn't depend on how you made it. So they're universal properties of gravity and space-time. And so by understanding the constituents of a black hole, we think that we understand something about the structure and nature of space-time itself. So that was one of the problems. I haven't told you what these constituents are yet, or what some of our current understanding of those constituents is. Now I'd like to describe for you the second problem, and this is the problem of information loss. So the idea is that we can form a black hole in different ways. So we can form a black hole with different kinds of stars, or we can throw information in the black hole in the form of books, etc. But the black hole will evaporate, emitting thermal radiation. And in Hawking's calculation, this radiation looked perfectly thermal and featureless, apparently independent of the initial state that formed the black hole. On the other hand, in quantum mechanics, if you form an object in different ways, it should evaporate, or it should decay also in different ways. Now, those different ways could be very subtle and could be almost indistinguishable, but there should be, at least in principle, some way to distinguish them. So if you take a book and you burn it, so the first approximation, you just have some smoke, and it would be, you apparently lost the information about the book. But if you manage to gather the smoke, in principle, some very advanced civilization might be able to figure out what was in the book, at least according to the standard rules of physics. And the question is whether the laws of physics that apply to gravity are also of the same nature. And in order to answer these type of questions, we really need to have a theory that puts together quantum mechanics and gravity. And a theory that does this and is designed to do this is called string theory. So I won't give you what string theory is. It's really a theory under construction. And it's a theory of quantum gravity, so it's a theory about the quantum mechanics of space-time. And it reduces to Einstein theory under ordinary circumstances, so at low energies or long distances. And it has many other features I'm not going to discuss. But one feature I'm going to discuss is that it can describe in a complete way certain simple universes which have negative curvature. And I'll try to discuss this in more detail now. But the main point is that it's a theory that describes the quantum mechanics of space-time. And also, it's a theory under construction. We don't know all its features. So there are some questions we cannot answer. For example, the question I was asked about what happens exactly at the interior of a black hole. Okay, so this fact that we can describe the interior of certain spacetimes in terms of theory at the boundary is called holography. And the idea is that you have some space-time. This is a picture of a space with negative curvature. So it's a picture that Escher, Dutch painter, drew. And here you should imagine all these fish as having the same size. So they all have exactly the same size. But we are projecting that negatively curved surface to a two-dimensional flat surface of the screen. And so because of that, the fish here far away are deformed. They are smaller. So this something similar happens when you project the surface of the Earth on a map. The regions near the standard projection, the regions near the North Pole and South Pole are blown out. So here they are all of the same size. And then the idea is that you have a gravitational theory. So the space-time has this shape, but it can have fluctuations. You can have gravity, you can have particles living in it. And all of that can be described in terms of a theory with particles living on the boundary. And the particles living on the boundary are very strongly interacting. This is another picture of the same thing. So we could have a particle moving in the interior of this space-time. The interior of this space-time has a kind of gravitational potential that pushes particles into the interior. So if you put the particle in the interior, they move roughly in this way. And this same particle is described alternatively in terms of the theory of strongly interacting particles. So here I try to depict the strong interactions by the rapid motion of these particles. That's what I'm trying to say here. And the interesting thing is that you can describe also black holes that live in the interior in a similar way. So the black holes correspond to a fluid, a kind of fluid of particles here at the boundary. Here I became tired of drawing these particles. There should be more. There should be a very uniform fluid around the boundary. The idea is that the temperature and entropy of the black hole comes from the temperature and entropy of this fluid of particles, that very strongly interacting particles that live here on the boundary. And when we discuss these strongly interacting particles, we know exactly how they're interacting. So we know the precise laws of physics that these particles in the boundary obey. They are hard to solve, but we at least know them. That's the idea. And the theory of the boundary obeys the rules of quantum mechanics. And so we say that then the black hole that lives in the inside also should obey the rules of quantum mechanics. So we think that black holes are consistent with quantum mechanics. Now, in this description, we have a kind of emergent geometry. We have particles that live near the boundary, and we have some geometry that somehow emerges out of their interactions. And this looks a little strange, and I'll try to explain this with an analogy. So it would be a verbal analogy, an analogy with words. So imagine a sentence. So let's say we have a sentence. Sentence is composed of letters, right? So we have the sentence reads, if a man does not keep pace with his companions, perhaps it's because he hears a different grammar. So that's a sentence. Now, you learn in grammar school that if you take a sentence, you can decompose it in the words. So unfortunately, you don't see these red lines here very well. So you can decompose them in words. Then you can decompose them in little phrases. They all have some grammatical names that I don't remember. And then in different subclauses and so on. And in this way, you are interpreting the sentence, right? So whenever your brain, when your brain hears this sentence, it's interpreting the sentence in this way. You automatically are doing this in your brain to interpret this sentence. And not only you have that, but you also have some long-distance correlations between parts of the sentence. For example, man is correlated with his, and is correlated with his. If here it said woman, here it would say her, and so on. And also, some concepts like the keeping pace is related to grammars, and so we have these various correlations within the sentence. Some are more short-distance correlations within the word, and some are longer distance correlations. So the idea is that the boundary theory produces a complicated state. We call it a quantum state, but it is the state of the particle. And the bulk is giving us a kind of interpretation of this state. It's giving us how the information in this state is encoded. And this structure of some smaller objects and some bigger and bigger and bigger structures is capturing the information present at different length scales in the boundary theory. So that's the idea. And then there could be some long-range correlation between specific words, like the words we had before, and those can be viewed as particles that propagate in that space-time. So that's roughly the picture. We have a picture like this, but a quantum mechanical version of this. That is how we understand the emergence of this extra dimension. Now we can ask now what is a black hole in space-time, in the space-time. So imagine that we had the same sentence that we studied before, but now we make some random changes. So there's someone that some editor is faulty and start changing some words. So for example, in this case, we changed a few words. So for example, the word it's and she and that. Okay? So now we lost some of the correlations that we had before. For example, before man was related to it, to his, and now it's not. So we lost that. And so this sentence makes sense. I mean, if you look at the small part of the sentence makes sense. But the whole sentence does not make the same sense that the previous sentence would. So we say that the sentence makes sense up to a certain level, and we say there is a black hole horizon. Beyond that, the sentence does not make any sense anymore. Now imagine we continue making changes. Right? So we made a little changes, and now the sentence makes even less sense. So it only makes sense for a few words, but then when you try to read it longer clauses, it doesn't make any sense. Then we say the horizon becomes a little bigger, the black hole grows. And finally, if you change all the letters, then it doesn't make any sense. Okay, you can recognize in the words, and the black hole grew even more. Now, the idea is that this area is the area of the horizon is the amount of ignorance that you have. So and the area growth is related to the fact that the area grows is related to the fact that if you change a sentence randomly, you are going to more likely mess it up than produce another nice sentence. And so as you start changing it randomly, the sentence is going to make less sense, and the disorder grows, and that's the growth of entropy. But now imagine that were produced by a reversible process. So imagine that this gibberish, or this random set of letters, was actually produced by an encoding process, like similar to the encoding processes that your computers do when you send credit cards over the internet and so on. The computers take that number and they mess it up, they produce some random set of things that they send over the internet. And so that if someone would like to read what was sent, they would just see this, right? So they would not be able to decode it. But if you knew the encryption algorithms, you would be able to decode the sentence. We can reverse that process and recover the original sentence. And that's analogous to the idea that you can recover the information from black holes. So the idea is that the laws of physics at the boundary change the state of the system at the boundary, and the laws of physics are reversible. So it's analogous to the laws of physics are analogous to an encryption process. They can be somewhat complicated, but they are reversible, and in principle we can undo the formation of the black hole, and in principle recover the original information. And that we can do in the boundary theory, because in the boundary theory we know that that's a reversible process. Okay, maybe I should ask for questions now. Yep.
When you say boundary, is that the same as an event horizon?
Yeah, so in order to have a precise description, you need to put this boundary very far away. We only know how to do this in a precise way when the boundary is very far away. So it's at the end of the universe. So you have a very, very big universe, and the boundary is at the end of the universe. It would be desirable to be able to do this for a smaller boundary. Let's say you take the black hole and you just put the boundary at the horizon. We don't currently know how to do that. So we can describe not only the black hole, but the whole space-time with the black hole. That's what we can describe in a precise way. Okay. Now, I said that the theories on the particles on the boundary are strongly interacting. And so you can use now the interior space-time to learn about these particles on the boundary. So in that analogy, we think about the boundary theory as the particles that live in our space-times could be a system of very strongly interacting particles. And we think of the interior as some extra, let's say, curved 5-dimensional universe. And it turns out that in this way, problems that might be complicated in the boundary theory might become simple in the interior. So the complicated quantum mechanical problem in the boundary theory can become a simple problem in Einstein gravity. So a simple problem solving Einstein's equations. And Einstein's equations are a little complicated, but it's easier to solve Einstein's equations than to solve the equations of quantum physics for strongly interacting particles. And so this is another way, let's say, of getting information out of black holes. We use black holes to learn something about strongly interacting systems. And this was used to learn, getting some insight about certain strongly interacting systems, like some phases of quantum matter, of nuclear physics. When you collide nuclei at very high energies, you produce a new phase of nuclear matter that you can view as creating a black hole in a weird 5-dimensional space. And then investigations in this direction have also led to some connections between black hole horizons and the loss of hydrodynamics. So as we said that on the boundary we have some fluid, and that fluid obeys the laws of hydrodynamics. And it turns out that the laws of hydrodynamics are contained within Einstein's equations. So when you solve Einstein's equations with a black hole horizon, you can find that they also include the laws of hydrodynamics, and there was some interesting development in that direction. So now I would like to talk a bit about the connection between entanglement and geometry, but yeah, are there questions? Okay, so we'll go into this other topic. So it turns out that in this whole discussion, there's a funny quantum mechanical property called entanglement, and it plays an important role in constructing the space-time geometry. And I will just try to discuss only one example. Maybe I should say a little more words of what entanglement is. So entanglement is a kind of correlation between two quantum systems, but it's a correlation which is a bit stronger than classical correlations. So you have two quantum systems. In quantum mechanics, you have a certain kind of randomness, but random results in this system are correlated with random results in the other system, but they are more correlated than they can be correlated in a classical theory. So I'll discuss only one example of this, which is the solution. It's essentially the same solution that Schwarzschild wrote. The solution of a space-time that is spherically symmetric with no matter. And this solution again took many, many years to be understood. We're only like 50 years after Schwarzschild wrote the solution, the right understanding of the solution was found. And the idea is that the solution doesn't describe one black hole, but it really describes two black holes. So there's a region of the space. This is a picture of the space-time. So vertical direction is time, and the horizontal direction represents the radial direction, how far we are from the black hole. And then there are two directions I'm not drawing, which are the directions of the sphere around the black holes. So the vertical direction is time, the horizontal is the radial direction. So this region far away here is the flat space region, and the horizon is this surface here. So the interior is this region here, and if you come from the outside, you fall into the interior and have a singularity here in the future. Here, the advantage of these pictures is that light rays are represented as 45-degree lines. So if you are someone traveling in this space-time, you always have to move at a speed which is not faster than 45 degrees. Now that's one black hole, and then we have a second black hole. It has its own horizon. And the funny thing is that these two black holes share an interior. So we have an interpretation of this as a kind of, this is described in a kind of wormhole. So we can have a black hole here, another black hole very far away, and let's say one black hole here in our galaxy, one in Andromeda galaxy far away, and they can be very distant in that space, but they can be sharing the interior. So they can be separated by a very short distance through the interior. Now I should emphasize that if you find two black holes in nature produced by gravitational collapse, they will not be described by this geometry. This is a very special geometry that is possible according to the laws of general relativity, and our goal is to try to understand what this geometry means. Now, these wormholes are not like the science fiction wormholes. The science fiction wormhole is a wormhole that allows you to go between this, between here and let's say Andromeda galaxy very fast, faster than the speed of light. Those things are not allowed by the laws of physics. They are not allowed by the principle of relativity of Einstein that we mentioned before, on which this theory is based. So we call this wormhole non-traversable. So you can try to send a signal from this wormhole, from this side to the interior, from this side to the other side. The signal cannot propagate faster than the speed of light, so it can only go along here, and it will fall into the interior, into a big crunch here, the singularity, and we will not be able to make it out of the other side. Now, the idea is that in the exact theory, each of these black holes is described by a set of microstates, so similar to this fluid of particles I was talking about before. So in the exact theory, this is described by a set of states, microscopic configurations, and also this one. And the idea is that this wormhole will arise whenever you have an entangled state, when we have a special entangled state. As I said, entanglement is a form of correlation in quantum mechanics. And so the idea is that there is this geometric connection from entanglement. And in order to try to explain this, I'll try to again go back to an analogy. So let's imagine that we have again the same sentence. So we have the sentence here in English, and here we have the sentence in Spanish. Now, here the correlations between the letters are different, right? So we have some correlations at short distances, but these are the correlations that Spanish has, and these are the correlations that English has, right? But both have this structure of some correlations at different distances, but the final meaning of the sentence is the same. So the fact that we have a common meaning of the sentence means that if we were to do an analysis, some kind of analysis of this sentence, we would reach a point where the analysis coincides between the sentence in English and the sentence in Spanish. And this is how we think about the fact that there is a connection in space between these two black holes through the interior, where we generate a connection between due to the correlation. Now, I said that this black hole is not useful for the typical science fiction story, but in order to explain what the weird aspects that these black holes have, these configurations have, I'll try to give you another science fiction story. So imagine that we are in some advanced time in the future, in some advanced civilization, and we have two people, one called Romeo and the other called Juliet, and they like each other, but their families don't like each other. So they try to keep them apart, and they put Romeo here in this galaxy and Juliet in some faraway galaxy. But Romeo and Juliet are very, very smart and very ingenious. And what they do is they exchange quantum qubits, quantum information, and they create an entangled state, and they create two black holes that are entangled precisely in this way. For this, they need very highly advanced technology that we don't have, and it's very hard to think how they would do that, but let's imagine they did that. So after they do that, then they decide to jump into their respective black holes. Okay? Then let's focus now on the bottom part of the picture. So their families just see them jumping into a black hole and disappearing behind the black hole horizon. So their families would say that they committed suicide because they fell into a black hole. And that's the narrator of the story would also say that. The narrator. But if we have this black hole, what they experience is different. They fall into the black holes and they actually meet in the interior because the interior is common. And so they would meet in the interior and they can live together for a while, and then unfortunately they died at the singularity. Now there's a way to rescue them, but I don't have time to explain it. It's actually proposed by someone here in the someone who's here in the center, Daniel Jeffries. Now, I explained so far the black hole as seen from the outside and the things we've learned about black holes as seen from the outside, but there are many things about black holes that we don't understand. In particular, we don't understand how to describe the interior properly. So the equivalence principle tells us there is no problem with crossing the horizon. And we have a mystery, which is how to describe, for example, the interior using the same variables that we use that make quantum mechanics manifest for the outside observer. So there are still many mysteries to be understood. So in conclusions, I hope to have transmitted to you that black holes are fascinating objects where the geometry of space-time is deformed in a dramatic way. Black holes and quantum mechanics give interesting theoretical challenges, and string theory describes black holes in a consistent way from the outside. We don't know the inside description yet. And space-time is an effective approximate concept which seems to arise from more elementary particles living in the boundary of space-time. At least this is the current picture that we can use to describe black holes in this way. And we also mentioned that the defining quantum mechanical property of entanglement plays a crucial role in determining the structure of space-time. Thank you. Probably still have some time for questions.
Yeah, we have time for questions.
Okay, so you brought up entanglement, but like let's say entanglement on a lepton scale, and you're looking at, wouldn't it be possible, I mean not a lot of data, to in a sense mine some data from paired electrons, if you will? So you would have one, you would know its spin, and then if one crosses over the event horizon, would you not then be able to infer or at least have some idea about at least some of the information that's in there, even though you can't get direct access to it, you know what it is based on the particle that you do have within your grasp, if you will.
Yeah, so if you have two entangled states and you throw one into the black hole, the outside state is still entangled with the black hole. So entanglement is preserved. I'm not sure if this is what you were asking.
Yes, that was.
Yeah.
On a very basic level,
Yes.
would you just define space-time when it's used connected in a connected language way?
Are you asking why we use the word space-time with time and space together?
No, I'd like you to define it.
I'd like to, okay. So space-time is a geometric concept, and it's defined in terms of the points on space-time. So we define a point in space-time as an event, something that happens at the place in space and at some particular time. So for example, the start of this talk was an event. It happened here and at some particular time. The end is another point. It happened at some other time, and so on. So we often represent space-time. Let's imagine space is one-dimensional. Instead of three-dimensional, just one dimension, just to visualize it more easily. And so we have the one-dimensional space and then the one-dimensional time. And we represent it this way. What this picture means is this could be some event. Let's say the start of the talk today at this location. Then we move in that direction. So in that direction there is another building. Here is the other building at that moment. The buildings exist for all time. So buildings are defined in some trajectories in space-time. So we have the trajectory of this building here and the trajectory of the building that is over there. If I turn on a flashlight here, I will send a signal to the other building. The other person in the other building will see the same. The signal propagates along all these points in space-time. And so this is the definition of space-time is a collection of events with some causal relation between them. So some are to the future of others, and also some distances between them. So we can say what the distance is between two events or the time that transpired between two events. That's the definition. So it's very similar to the definition of Euclidean geometry, Euclidean space. Yes.
You were talking about black holes having lifetimes.
Yes.
Are they on and then off, or do they become black holes and then lose their black hole?
Yeah, so the idea is that the black hole forms and then it starts emitting Hawking radiation. Because it emits Hawking radiation, it loses mass. It becomes smaller and smaller and smaller. And then in the final process, it emits radiation more faster and faster, and it's a big bomb. It explodes. That's the lifetime. Yes. Yeah.
In quantum optics, when we have entangled photons, at an earlier time, those photons came from a common point or a common origin.
Yes, very good.
You seem to, when you talk of black holes being entangled,
Yes, yes.
are you implying that at some earlier time, those two black holes came from the same place?
Yes. In order to produce them in an entangled way, you would have to have they would have to have a common origin. So, for example, when I told the story of Romeo and Juliet, I said that they exchanged entangled pairs, so you produce the entangled pairs as you could do in quantum optics, and then send them to each other. And then I'm assuming they have an inordinate, wonderful quantum computers that allow them to form the black holes in any desired state. We don't have such quantum computers. Yeah.
So when you're talking about the black holes ending their lifetime, because they emit Hawking radiation,
Yes.
what happens if they keep like eating up more matter?
Yeah, so if they keep eating up more matter, they will live longer. So if you could have a situation where you have a black hole that is emitting radiation, and you emit enough matter to account for the radiation that is emitted, and then that can live forever. Yeah. Or you could put, for example, a black hole in a box, right? And then the radiation that is emitted falls back into the black hole, and that also can exist forever.
You said earlier that trajectories function so as to maximize the proper lifetime of moving particles. Is that related to least action?
Yeah, that is the least action.
So it is?
Yes. Because the action for a particle is the time. It's the time, proper time of the particle. It's the time that the particle experiences. Yeah, that's the time. Yes.
You showed the image from Hubble telescope of the black hole.
Yes.
And you showed that light was like coming out, or you mentioned that particles going into the black hole are emitting light.
Yes. They form when they fall into the black hole. The point is that there are lots of particles falling in.
Yes.
And they form a gas, and the gas gets compressed and heated. That heat is what is emitting the radiation.
Why do they form the gas?
Well, there are lots of particles, so they bump into each other and they interact with each other.
And that's the source of the heat.
Yeah. It's like many people trying to rush out of the room.
On that note, let's thank Juan for his lecture today.